Hello everyone, I'm Cedric from MDPI and I will be your host for today. Welcome to the second live session of the 8th International Electronic Conference on Sensors and Applications, ECSA 2021. This e-conference is hosted online from the 1st to the 15th of November 2021 and is organized by MDPI and the journal Sensors. During this time, the conference presentations will be available for discussion on the conference website. The accepted extended abstracts will also be available in the journal Engineering Proceedings, and the journal Sensors will publish a special issue of the conference proceeding papers. I would like to thank the conference chairs, the conference committee for making this e-conference possible, along with the speakers and, of course, our attendees. I would like to remind everyone at this point that this webinar is being recorded, and the recording will be made available as soon as possible on the webinar's webpage. Today's session is also being live streamed on MDPI's YouTube channel, so hello to those of you watching us on there. Today there will be one keynote presentation of 30 minutes and 5 selected presentations of 15 minutes each. The presentations are followed by a question time moderated by the chairs. If you have any questions for our speakers, please feel free to post them in the Q&A box, which you can find by clicking on the Q&A option at the bottom of your screen. And today's live session is chaired by Dr. Francisco Falcone from the Department of Electrical and Electronic Engineering at the Public University of Navarre in Spain, and Dr. Alberto Vallan from the Department of Electronics and Telecommunications at the Politecnico di Torino in Italy. Thank you both, Francisco and Alberto, for chairing this live session. I now hand over the mic to you, and I hope you all enjoy. Thank you.
Okay, so good morning, everyone. Thank you, Cedric, for the presentation. And thank you, all of you, for joining this second live session of ECSA. This is the eighth edition of ECSA, which I think it's a really great milestone for the conference. So I'm very happy to be with you today, and also with my co-chair, my colleague, Alberto Vallan. And I actually will hand the floor to him so he can provide us the presentation of our keynote speaker, Dr. Ulm. Thank you so very much, Dr. Ulm, for your kindness and your time. And I'm sure that we're going to have a very, very nice speech from your side. Also, I would like to thank all the rest of the speakers of the session. And we'll keep on with the session as soon as possible. So, Alberto, the floor is yours. Thank you very much.
Okay. Thank you, Francisco. It's time to start with our guest, and then afterwards we will have 5 presentations. It's my pleasure to introduce you Dr. Markus Ulm, which is the Chief Technical Officer of Bosch Sensortec, Germany. As you know, Bosch Sensortec is a leading MEMS technology specialist that is very active in the sensor field. Dr. Ulm is responsible for research and development of sensor based on microelectromechanical systems, MEMS, for consumer electronics and related industries. Markus has a master's degree in physics from the University of Oregon and a diploma degree in physics from Karlsruhe Institute of Technology. He continued his study in the field of MEMS and graduated from the University of Stuttgart with a degree in semiconductor technology in 2003. During his career, he held various positions in the field of MEMS, semiconductors, and sensor research and development in the Bosch Group, such as a section manager in the Bosch Research and Technology Center North America, section manager for automotive gyroscopes and IMUS, director of sensor pre-development, as well as VP for consumer sensor product development. The title of Dr. Ulm's presentation is Technology at the Edge of Everyday Sensor, which sound really interesting for us and for the audience. So Dr. Ulm, thanks again for accepting our invitation, and please, you can start your talk. Thank you.
Thank you so much for the kind introduction. Thanks again to both of you, Dr. Falcone and Dr. Vallan, for the kind introduction and for the invitation. Cedric, thanks to MDPI for hosting and organizing this event. The title of my talk is Technology at the Edge and Everyday Sensors, and what I mean with this and why it's important to me, I will point out in the following 30 minutes. Brief outline. I will quickly introduce myself for the company, but I promise you this is only 1 or 2 slides, and then I go into pressure sensors, inertial sensors, gas sensors, magnetic sensors, and conclusions. Since I have only 30 minutes and you guys are the scientists, I assume there's many people attending from all over the world. I will keep it more on what I find personally fascinating in the field and why I think it's highly relevant for industry and academia and science to work on this and stay on an overview level, but give you some examples why I think it's a fascinating field and why it's generally a little bit underrated in public funding or in the overall semiconductor discussion. Let me start with a quick introduction. As Dr. Vallan pointed out, we are a company focusing on consumer sensors and with a relatively broad portfolio. We have multiple motion sensors. These are sensors centered around inertial sensors and magnetometers with or without microcontrollers. We have a class of environmental sensors, starting with the pressure sensor, but also including humidity and gas sensors. Smart sensors are combinations of motion sensors with different classes of microcontrollers. And then we have one field with the optical microsystems, where the most prominent one is our smart glasses life drive project. In addition to this, which is mostly centered here around MEMS technology or some transducer technology plus ASIC, ultra high performance, ultra low power designs. We have a cross-cutting segment where we focus on algorithm, software, tool, and embedded AI. I don't have any extra slide on locations. So we have strong design centers in Europe. In Milano, for instance, we have a strong design center, but also in Munich, Dresden, Shanghai, Suzhou, Sunnyvale, all over the world. So if you're interested, please get in touch with us. As Bosch, we are active in both fields. We are active in the field of, maybe I turn this down. We're active in the field of classical consumer applications like step counting, image stabilization, indoor-outdoor navigation, and so on, augmented reality. As a Bosch group, we also cover things in the automotive or in park spot detection and so on. I think this in a nutshell. And now I would like to move on to the more core content of my talk. And let me start with a little look into Google Trends, which I just did last night. And is our segment still relevant? And I like to look at Google global coverage, just see what do people still Google. And one of the things that is Googled quite a bit is of course AI. So I use this as a reference with this, which is 100% here in a certain spike. Maybe this is when Elon Musk mentioned AI or whatsoever. And this is the purple line, and you can see the green line in comparison to that. So over decades, the interest in sensors globally has been really high and is still increasing. So I think we do work in a very relevant field of public interest, because we are the ones that, as a sensor community, that give devices and machines the sensors that are needed for interaction with us and for completing the core function. If you look in the curves down here, this is if you go one level down from AI to machine learning, or from sensor to MEMS or wearable and so on, you can see the same picture. Also here, there's a constant global interest in MEMS, wearables, machine learning is spiking a little bit here, but I think MEMS is also a much more specific word in machine learning. So key message here, very relevant topic, and please, I think you pick the right field, the right conference, and I hope you can build and continue to build your career on this. This was more from a sociological point of view. Is it relevant? Is this of interest? Of course, we also need to look at the market numbers. And here I like to cite some numbers from Yole Development that they provide in their regular forecast. And what you can see here is global MEMS revenue in dollars. So overall, it's a very relevant industry with still significant growth, roughly 7 to 8% CAGR over the years. And also our segment, like the consumer segment, is a multi-billion dollar segment. I have to admit that consumer MEMS, of course, also it's not only sensors, it also includes some RF parts or other things which do share some of the same technological challenges and technological contents as we have. So key message, highly relevant field, same picture as from the sociological view. So now what bothers me a lot is that I do think we are underselling ourselves in the sensor community. And part of this has also to do when we as a company look at things, we have slides like this, we have some use cases and applications which people know. And then we have these black little things and you don't really see any technology inside. Once my kid asked me, what are you doing? So why does it take you so much time in the office or on your work? This is less complex than a piece of Lego, and it looks like it being less complex. Of course, you as scientists know. And I want to spend the next 25 or 20 minutes on pointing out why I think this is really a fascinating field and it doesn't need to hide from 5 nanometer semiconductor technology or other topics which are really currently in the focus. I would like to start my example with pressure sensors. And since we're in a wearable session, I would always like to compare what's the ultimate benchmark, or why do I think we still also have room for future achievements in that segment. So in the following examples, you always find one example out of nature, and then where do we stand with technology in reference. So pressure sensors, surprisingly enough, it's well known in the animal world that people actually, and not people, but mammals or like also birds actually use this to manage their daily life. So seagulls seem to have a special nervous system with some type of air bubble whatsoever included to sense pressures. And they use this in order to escape from storms and strong winds. So they detect strong pressure drops in a couple of 100 hectopascals. There's other animals like bats that they do it in the opposite way. So before they travel, they look at a strong increase in pressure. And even so, if they have a headwind, they start based on this strong increase in pressure. So you known from the animal world. So what do we do with it? Consumer industry looks at this from the perspective of more activity tracking, body motion tracking with pressure sensors. And what I show you here is typical height changes if you do certain fitness exercises, for instance, in your ear or your wrist or mounted to your arm. And what you can see is that a lot of these activities can be classified with height changes in the order of 60 centimeters, which is, it's a lot less in terms of pressure that we have to sense than the animal. So there we really have some tightened spec compared to the animal kingdom. Push-ups, it's a similar picture. So you need to have a resolution in the order of a couple of centimeters to be able to classify activities like this. Of course, there's other applications than body motion trackings like 9/11 and so on. But the key message, very high accuracy needed. And in order to do that, it actually takes quite a bit of technological effort. And I can show you here as in an example from STEP. So this is a new capacitive sensor technology. And you can clearly see the steps resolved. And one step height here is 17.5 centimeters. And so what does it take in order to be able to resolve these 17.5 centimeters? Just to keep in mind, this means 17.5 centimeters on top of an air column, which is already 13 kilometers high. So this is resolving 2.1 pascals on top of 100,000 pascal. Or it compares to weighing an air change of 17.6 micrograms, a thousandth of a mosquito on top of this membrane, or a capacitive change on 12.6, which of course you still need to resolve. This corresponds to not more than a few electrons. It's less than 100. And I think this is really amazing that actually a consumer sensor device, which is relatively competitively priced, can resolve such a significant measurement precision. And you use this and find this in your smartphone every day, but you only few people understand what's actually behind this technological function. In the following, I like to do soccer examples for whatever reason. And so if you compare this pressure sensor membrane, capacitive membrane, with a soccer field, it roughly has a scaling factor of 1 million, not exactly, but that would mean the deflection of 5.9 picometer of this membrane to resolve a step equals to a change of deflection of a soccer field by 2 hairs diameter. So really nice piece of technology to get this done, and for me, very fulfilling to work on things like this. Let me move on to inertial sensors, and there I again would like to start with an analogy from the animal kingdom. My most favorite animal there is the squirrel, which actually has an extremely good equilibrioception. So and it does it really well with video fusion. So they can, of course, you know how well they move through the trees, but also if they jump or fall, they have an extremely well-balanced sense of doing video fusion, having their head oriented to the target and still move their body in a very controlled way to always land in the right position. Maybe cats and others do it in a similar way. If you like to dig into this a little bit, there's a very fun link from Mark Rober on the squirrel maze, and there you can find some of the animal achievements. How do they manage flights or jumps and so on? We found out that actually NASA used one of our sensors, classical consumer sensor with a good balancing between power, performance, and robustness to also manage flight in NASA's Mars helicopter Ingenuity. Of course, the movements are a little bit less elegant than the one of a squirrel, but on the other hand, it's on Mars, and the robustness challenges there are quite different. So I'm really happy and enthusiastic that our MEMS devices with the robustness and precision that we as an industry and its company achieved over the years was capable of supporting this experiment on Mars. Now to my beloved soccer examples, if you look on an inertial sensor and you compare the seismic mass to a steel plate on a soccer field, what you actually do is you have then roughly 100 meter metal plate, which is a meter thick, and you have that oscillating on top of the ground, and the gap to the ground is 10 centimeters, and you have to control this gap with 0.7 millimeter precision. That's quite a challenge if you imagine it, but there's other things too that I think which are truly challenging. If you look on a sensor here in an application, typically, as we will later on see, temperature changes and TCO calibration is an important topic. But not only that, you also have to deal with temperature gradients. Why is this? The temperature here is, of course, never homogeneous, and so you do have a certain temperature gradient over your sensor. And if you have an asymmetric sensor, like you typically use the theta toroid, for instance, in Z-channel things, there's different gas pressures or radiometric effects on the mass here, and you do see an offset as a consequence of this. To overcome this as an industry, we came up with a three-dimensional structure where we have an asymmetry in the mass. I have a differential readouts which are fully symmetric, and also in terms of radiative effects, this is a completely balanced structure, so you don't see any offset anymore. The one here, which is asymmetric, you could even use it to sense different gas contents. the balanced structure has a factor of 100 less dependency on this radiometric pressure. So this is an example where, just as a side effect, we are already at a precision level where the radiative effects have a significant performance impact, need to be encountered. And it's a little bit similar example as this fascinating solar mills that you have running in vacuum, where the radiative effect drives this thing forward. So on the gas sensor side, I cheat a little bit. This is the sense of taste, smell, and I combine this. Here in European eel can taste a single droplet of perfume in an area which is, or a volume actually, which is 11 times bigger than Lake Como. I also really think this is fascinating, and if you calculate it, it's roughly 2,000 atoms in a square centimeter of water. There's still a couple of orders of magnitudes more precise than PPB type of sensors. What do we do as an industry and as a company to achieve these type of precisions? We have elaborated ultra-thin hot plates where we heat metal oxide sensors. There's actually an excellent talk also tomorrow in this event, which gives an overview on the development of these sensors. And since we have a really fast reaction time, we can heat up to 400 degrees in 20 milliseconds. We are actually able to control the temperature and cycle it to increase selectivity and performance of this device. Also here, it looks like a harmless little droplet on a membrane, but if you zoom into it and make some cuts, that you finally find out that the real secret and the science is hidden in the grain boundaries of the tin oxide grains, where the gas actually alternates the mobilities, and you can use this as a sense effect to classify gases combined with some complex algorithms. An application example is, of course, advanced fire detection. So you can use this and with sensor networks to get an ultra early fire detection where you don't really have a lot of smoke, but just the initial phase where you can smell it but not really see the fire. And there's applications out there, a company called Triad Sensor Networks, for instance, which builds sensor networks to actually do this. And you can use advanced algorithms and AI functions to do classifications to separate a real fire from other side effects. And we really close the cycle here that you can also, out of the learnings you've done here, go back and update your AI algorithms to make sure that you have good read-ins, good coverage of fires, but also an avoidance of false alarms. Let me finish my series of examples with the magnetic sensors. Here it's well known that, for instance, pigeons use this, or birds in general use this to organize their flights. But actually this is a way older story in evolution. So it seems that even some bacteria, which are more than 1 million years old, have some sensitivity where they use proteins with some ferrum connected to it to sense actually orientation. So the initial bacteria that used this used it for up and down. Now the animals are smart enough to use this for traveling and absolute orientation. Unfortunately, I don't really have that sense, but I'm still fascinated how nature incorporated. And of course, we also as an industry are chasing nature to make a solution which is as good as this. Another important example is honeybees that use also Earth magnetic field for both inside and outside the hive movement. What we as an industry and as a company are currently working on is Team R sensors. Of course, there's solutions like Hall, AIM-ARM, GMR, which are excellent magnetic sensors. But if it comes to performance over power consumption, Team R is unmatched. And this is especially for the wearable segment for us, the goal to have a 3-channel sensor here that is capable of having an extremely high figure of merit, performance, noise versus power. Just to give an example, what we're doing here, trying to do here is measure, for instance, in Reutlingen, a 22 microtesla magnetic field for the background of hard magnet offsets, for instance, by loudspeakers of 700 microteslas, but also noise from the building, 40 microteslas, some self magnets, 200 microteslas. And the goal here is to have a sensitive enough sensor with a high enough dynamic range to avoid complicated calibration algorithms. In order to do something like this, you also really need to drive technology to a limit. And an oversimplified picture of a team R stack is actually a free layer that orients itself to the outside magnetic field, and a reference layer and a tunnel junction in between. And this tunnel junction, the tunnel current is modulated by the orientation of the free layer. And to make this a highly functional device, it's all about this insulating layers and the ferromagnetic layers and the layer quality here. And in order to do this, you need to have something like atomic layers. And if you compare this on a wafer scale, that means you want to have a precision of 0.5% across the wafer, which is 8 picometers. So roughly speaking, you want to have a precision of 1 atom homogeneity over the wafer on your 10 atom layer to get high performance functional devices. I like to close this series of examples on how exciting our field of sensors is with the last soccer example. This would mean that the standard football field we would require to be the lawn mode with an accuracy of 1.8 micrometers, which is should illustrate the challenge quite a bit. So with this, I would like to come to the conclusion just around time. And so what do I want you to take from this overview talk through the last 30 minutes? It's mostly that sensors remain a very fascinating field for many years to come, and your contribution is highly welcome. At first sense, it looks like that magnetometers, pressure sensors, inertial sensors are mature technology. They have been around for quite some time. However, I think if you look at it from the perspective of performance and robustness versus power and size, there's still a lot that our industry can do to make these sensors better, improve, make them be a more reliable partner and less power consumptive partner in our customers' devices. And there is room for future achievements for many years to come. And I think it's our joint effort as academia and industry to transport all the fascination of this topic in order to keep on attracting excellent engineers and scientists to propel this topic also in the future. So thank you very much for your attention, and I hope I could bring across my personal enthusiasm for the field, and I'm open for questions.
Okay, thank you. Thank you so much, Dr. Ulm, for your very, very interesting presentation. We have time for questions. While we are waiting for a question from the audience, I have a question for Dr. Ulm. I was really impressed by your sensor performance, the pressure sensor mainly, which has an extremely high sensitivity, and I suppose with a very small noise and with a very small power consumption. So I'm curious about the calibration of this very accurate sensor. Are these sensors calibrated, let me say, by design during the production, or do you trim the sensor in some way? Do you calibrate each sensor or not? What is it?
So I think the generic answer to this is actually you need to do both. So there's a lot of extensive simulation and system design work to make the sensors excellent in the first place, even before calibration. But then there's also a lot of work in what do you use as a reference, and how do you and I cannot go into the details of how we actually do this, since it's competitive, but what I can comment on is that, of course, we do need to calibrate each sensor, and it's a piece of art to also have suitable references in high volume production, because today's consumer sensors are getting extremely close or are better than things that you can actually buy for a factor of 10,000 more or even higher as a reference sensor. So it is a challenge, and you were pointing at in the right direction.
Okay, I understand. Thank you. So questions?
And there's one from Javier Burgues saying, hi, Markus, great presentation.
So the question here is, I defined some type of figure of merits for the physical sensors, but in the gas sensors, I kept it rather short. The comment on that is that what I do on the gas sensor side, I was using an example where it was also about classification. So MOG sensors are less sensitive in a sense than purely optical sensors, but they consume less powers and are able to be integrated in a much smaller volume. And there, the proper means of giving a figure of merit most likely would have been a convolutional matrix on the classification. The solution that we offer here is an AI suite, where the customer actually has an impact on the classification quality by its training data. So it's a little bit difficult to give a generic figure of merit for a declassification device, which is then highly influenced by the customer. I hope this this gives you some background. So then there's another, or future improvement for gas sensors. For me, it's I'm committed to drive metal oxide sensors forward, and as I pointed out, our current focus is on achieving means on how to do the classification better, and of course also having some quantitative means, but it will be a combination of improved classification with quantitative means, and for us that would also involve in looking into different chemistries combined with more advanced cycling methods and AI methods to make progress here.
Okay, thank you. Other questions?
Yeah, there's one more that has just come in.
Okay.
From Teresa Scholz. So it says, did you manage to use the MOX sensors for live classification? This is classifying while streaming the signal. Thanks.
Live classification. So the so if the I try to rephrase the question to make sure I understood it correctly. So if you have this MOX type of sensors, you could do two things. You could stream the sensor data and then do the inference AI in the cloud. You can do it live on the edge. So this is now another on the edge. And what we do is actually we do it live on the edge. So the inference and the classification is done directly at the device or in the sensor node. Of course, there's then a check of the models and so on. So you can update the models. This was the other stage that I've shown. But it's live and at the edge of the cloud, so to say, not in the cloud. I hope this answers the question. So.
Yes, thank you very much.
Yeah.
So we do have more questions. So we do have one more in the
Yes,
in the Q&A.
This is a topic for a talk by itself. So personally, I think at the beginning, it will, of course, like the role of the sensing hardware and the ASIC, ultra high precision ASIC design and all of this, I think has been covered of talk. And now if this is meant in a sense of how is the compute part, yeah, it says here, So my personal opinion is that for some time to come, at least in the industry side, the focus will be on driving the tool chains and algorithms forward and use conventional microcontroller architectures to achieve better performance. So it will be more scaling the models and improving them. And then in a later phase, we would also look on more advanced stuff like in-memory computing or analog computing type of things. So on the long run, to achieve ultra low power, I think this is something that will come. For me as an industry, I think it's still a little bit out, an industrial partner, but I think it's a great topic for academia and for scientists to work on this and drive this forward. So.
Okay, thank you. We do have also one question in the chat, and it says, to which degree has the fire detection method with gas sensors already been tested? Are there already preliminary results available?
I think yes, so I think what I can comment on that we use a sensor like this also for a Bosch product on fire detection. So it's combined with another method as well, but we have done some internal results, but I think our security department does not publicly share this, but I can confirm that it's tested. And for the other application, the company Triad Networks, you can check on the internet on where they stand with system verification and system deployment.
Okay, thank you very much.
Okay.
Are there any additional questions or?
I'm still curious about the trend in the market concerning consumer sensors, sensor for consumer electronics. What is the main request from the market for a sensor with a very small power consumption, with higher accuracy, higher sensitivity, and what else? I understand that these are interconnected features. So if I want a very small power consumption, I will have a higher noise. And so, what is the market demand for this?
I think exactly as you said, it's the overall figure of merit. So if I want to oversimplify it for multiple sensor classes, on the numerator side, it's performance in whatever means, offset performance, noise, and robustness. And on the denominator side, it's size and its power consumption. And the art is to scale all of this to make of course, you can, for instance, if I look at an inertial sensor, increase noise performance by just making the device a lot larger, and so on. So, but it would be kind of cheating. So the art to make it a device which doesn't really need a lot of resources and can be integrated, for instance, in an in-ear headset and so on, is really to tackle all of it. So robustness, power consumption, performance, and size at the same time. And I think that's a trend, at least for me as a consumer industry player, which is the leading scheme to have all of this covered.
Okay, thank you. So
robustness includes, of course, also reliability and other facets, which I did not explicitly mention, but which are extremely important for our industry as well.
Stability of the performance,
yeah.
I suppose.
Yeah.
Okay. So Francisco, we don't have other questions?
No. I think that the audience has already posted all the questions.
Okay. So we can thank again Dr. Ulm for his time, his very interesting presentation. So thanks again.
Then thank you very much for your interest, and thanks a lot for all the great work you do as a sensor community, which allows us to drive things forward. Thanks a lot.
Thanks. And we can now move to the next presenter.
Mm-hmm. Yes, so thank you once again, Dr. Ulm. Thank you very, very much. So then we move on to the next paper. I would just like to clarify one thing for all of the speakers. The way in which we will proceed now is we're going to follow the program, and the program says that each one of you is going to have approximately 50 minutes for the presentations, and then we will do a joint questions and answers at the end of the session, okay? So keeping this in mind, our next paper is entitled Temperature Stability Investigations of Neural Network Models for Graphene-Based Gas Sensor Devices. And this paper is going to be presented by Sebastian Schober, which is with Infineon Technologies in Munich, and also with the Institute of Integrated Circuits, Johannes Kepler University in Linz, Austria. So Sebastian, the floor is yours. Thank you very much.
Thanks a lot. Welcome to our presentation on temperature stability investigations of neural network models for graphene-based gas sensor devices at ECSA 2021. My name is Sebastian Schober, and I will present our work on this topic, which was done together with Yosra Bari, Cecilia Carponelli, and Robert Wille. So air quality, especially in cities, is a more and more important topic in the public discussion. And therefore, technologies are necessary in order to track air quality on a large scale. This can be done, for example, by sensor networks with many nodes to cover a wide area. And one technology which is quite promising in this regard, since it has a lot of advantages in costs and production and scalability, are chemiresistive gas sensors, such as, for example, classic MOX sensors, but also sensors using materials such as graphene to measure gases in the air. The working principle behind such sensors are changes in their electrical properties when gases adsorb onto the sensor surface. For example, this can lead to a change in conductivity or in resistivity, which can then be measured. And this is basically the pipeline that is performed here. So we have the adsorption on the sensor surface, then we get a resistance or conductivity signal. And after that, this information can be translated into a gas classification or concentration prediction. But for this last step, pattern recognition algorithms are needed in order to make sense of the different signals measured by the sensor, as they often come in sensor arrays. And a very common algorithm well equipped for these tasks are neural networks. So, of course, there are also drawbacks when using such types of sensors compared to other solutions. For chemoresistive sensors, often long-term stability is an issue, such as drift, which is a well-studied topic already. But also in the production process, there can be factors which have an influence on the overall performance of these sensor algorithms. Here they are called sensor-to-sensor variations. And one example of such variations that can occur from sensor-to-sensor level can be heating calibration or small changes in the sensitivity of the surface to a certain gas, or also in terms of long-term usage, that there are different aging states of sensors. And basically it can be summarized that there can be physical properties or calibration features which might be slightly different from sensor to sensor level. And all these factors can lead to a certain problem of transferability. So when we train an algorithm on one sample sensor and then deploy this algorithm to another sensor, which might have slightly different properties, and even if these are rather small, this can have an impact on the sensor performance overall. And in terms of algorithms, we might therefore have a distribution problem, so to speak, as you can see it on the right side on the slide, as it is illustrated here, that the input distribution of the sample sensor is slightly different than the input sensor of the new sensor on which this algorithm is applied. And in our research, we wanted to investigate, therefore, two different questions, specifically for the variations in temperature, as I stated it in the examples. So the first question would be, how much can a different heating calibration influence the prediction accuracy of our pattern recognition algorithm? And secondly, we also wanted to study if the robustness can be improved of the algorithm by more diverse data sets, including different heating schemes. And in order to do this and to answer these questions, we used a gas sensor simulation model from previous research, which can basically create synthetic signals for different concentration and heating settings. And this simulator is based on different Markov processes, which model the adsorption and desorption behavior on the sensor surface for different gases. And basically, the inputs of the simulation are a gas concentration profile. In the scope of this study, we use ozone, as well as a temperature profile for the temperature modulation of the sensor. And as an output of this simulator, we get then a set of 3 different simulated gas sensor output signals, which represent the different functionalizations in the sensor array. So now we come to the methods. So you can see the data setup of our study. Basically, we simulated 3 different ozone profiles, which you can see in the first row of each plot. So this is kind of the ozone distribution over time. And the other plots show the simulation output of each profile for different heating conditions. So the second row of each plot shows the 3 output signals at the standard heating, which means that delta T is 0%. So we don't have any deviation from the original temperature settings. The second row shows them for lower temperature, where the temperature is 15% lower than in the usual temperature settings. And the third row shows the 3 signals for higher temperatures with plus 15%. And but of course, also other temperature variations have been simulated for these profiles. This is just an illustration on which type of data we used. In terms of pattern recognition methods, we used a recurrent neural network with 1 hidden layer. And in this hidden layer, we used 50 GRU cells. The data that were used in the input layer of the neural network were the relative resistance, which is the standard output, so to speak, of such a sensor, and its derivative, which is also often an input for such algorithms, and also the energy vectors of each combination of signals. So now we're coming to the results. So in the first question, we wanted to investigate at which temperature variation we would see significant performance loss of the sensor algorithm. So there we wanted to test what is the margin basically in which these temperature variations aren't having a big impact and at which threshold basically the impact is visible. And in order to study this, we trained the algorithm with 1 profile at the standard temperature settings, and then tested it on the test profile simulated with several heating temperature settings. And the evaluation was performed individually for every temperature variation. And this is basically what you can see in these plots. So the plot on the left shows the performance metrics for negative temperature variations, and the one on the right for positive temperature variations, hence more heating. And as metrics, we used RMSE, root mean squared error, and mean absolute error, and as well as the standard deviation and the R2 score. In the plots, you can see that with increasing deviation from the standard temperature setting, we notice a steady decline in the model performance in terms of all metrics tracked. While at 5% deviation, the performance seems to be comparable to the normal settings. At around 10%, we notice significant changes for all the metrics. And a second observation that we were seeing there in the data was that this effect seems to be stronger for positive temperature variations than for negative ones. And yeah, so like positive temperature variations might have a bigger impact because it changes the overall signal. It seems to change it a bit more than having lower temperatures overall. Yeah, and for the second experiment, we wanted to check if these this changes if we use a more diverse data set for the algorithm training. And there we simulated profiles with 0% deviation, minus 10% deviation, and 10% deviation for the temperature settings as part of the training data. So basically, we had two neural network models. One, as usual, with only the standard parameters, where we only used 0% deviation simulations for the training. And the second one, basically with several heating parameters, where we simulated the profiles with 3 different temperatures and used all these 3 settings for the training. And then we compared this again for the different test profiles. As you can see in this plot, this change in training data caused that the model trained on the diverse data set, which is always the right column in each data point, basically for the root mean squared error and the mean absolute error, so this diverse data set outperforms the single temperature model in every test variation case, even for 0% deviation, where one might think that the original parameters might have a better performance. But overall, this substantiates the claim that model robustness was improved by using different temperature settings. And therefore, this experiment indicates that a well-balanced data set can at least partially compensate for such sensor-to-sensor variations, and that it might be worth to really train with several temperature settings. So as a conclusion, our first experiments or our first study substantiates that a significant algorithm performance loss can be seen for temperature deviations above a certain threshold, around 10% in our simulations. Furthermore, a certain improvement of algorithm robustness might be already achieved if we use a variation diverse training data set. But however, there are additional simulation and experimental studies needed in order to further substantiate the findings, especially for more complex settings and other profiles. Thanks a lot for your attention, and I'm looking forward to your questions.
So Sebastian, thank you very much for your interesting presentation and for sticking for the time perfectly. Thank you. So as Cedric has already stated in the chat, please remember that all the questions, let's pose them in the questions and answer section of Zoom. And what we will do is that we will go on with these questions and answers at the end of the session, okay? So taking this in mind, thank you once again, Sebastian, for your presentation. And we now are going to move on to our second presentation. So maybe Alberto, you can.
Okay, thank you, Francisco. We can move to the next presentation concerning a gamma ray sensor. The title is GEA-NT4 Modeling of Ambient Temperature Perovskite Gamma Ray Sensor. The presenter is Charles An. Charles An is with the University of Nevada, Las Vegas, USA. So let me see. Okay. Hi, Charles.
Hello, everybody. Thank you for joining the 8th International Electronic Conference. I am Charles An for University of Nevada, Las Vegas. Today, I'm going to show you our GEA-NT4 modeling of ambient temperature perovskite gamma ray sensor. So we'll see these content in this presentation. First, we'll check our kind of gamma ray sensors commonly used these days, and what is perovskite, what is their properties. And now I would like to introduce Monte Carlo modeling of radiation transport. And we'll talk about our objective, which is the development of our computational model of perovskite gamma detectors. And then talk about method, including GEA-NT4 and root. After that, we'll discuss our research, conclusion, and future work. So in this day, there are many researches for radiation detector technology. For the required demand on good performance, it is necessary to improve their properties, especially high energy resolution and sensitivities. We got here high purity germanium, cadmium zinc telluride, silicium bromide, and these materials usually used for radiation detector in many fields, such as national security, aerospace, biomedical industry, and scientific researches. Their performance is good because they have a high electron density, high sensitivity, and big energy gap. But the problem is they are hard to make. So such traditional materials have difficult crystal growth conditions, so it causes defect in their microstructure. So it makes the detector performance bad. So cesium lead bromide is our choice because it has perovskite structure, which have high mobility lifetime product, low defect densities, and long-term stability for photon and charge particle detectors. Many studies was reported a stable crystallization method of cesium lead bromide with great properties, but the size control is unstable during the crystal growth, so that the cesium lead bromide crystal remains in a small volume now. That's why we focus the study of large size perovskite detectors, including the computational models. So we selected GR4 toolkit to build up our perovskite gamma detector model. You can see Monte Carlo's method consists of normalized density functions and rejection functions, which allow simulation algorithm to calculate random sampling. GR4 toolkit uses this formula for the computational calculation. On the process flow, the scheme of GR4 categories shows what kind of class GR4 can take care of. GR4 can configure a lot of simulation variables, such as control of geometry and materials and particle interaction in matter, tracking management, digitization and heat management, event and track management, visualization and each framework, and user interface. So with GR4 simulation class, so we know GR4 toolkit uses Monte Carlo's method, which is a simulation statistical algorithm based on the random sampling to calculate numerical results. Our code controls geometry and materials class connected to GR4 physics libraries for our desired results. Our computational model was configured by cubic 8 centimeter cube crystal. So with the simulation variables, gamma ray transport was investigated through this perovskite detector model, and Root toolkit visualized our data. So here is our method. So in this table, you can see more detailed parameters for our study. To configure perovskite structure model, cesium and lead and bromide were designated with their atomic number, standard atomic weight, and compound density. So after big size cesium lead bromide crystal came from, our gamma particles coded with QGSP physics library, which uses the low energy parameterized model for all particles. For the precise results, 1 billion events generated. So let's see our results. We can see the cubic perovskite crystal developed perfectly. 1,000 and 2,000 events selected for the sample view because 1 billion events builds up each gamma rays in whole space. So we can see green gamma ray penetrates our model in each event. The results show gamma ray spectrum from our giant force simulation data using Root Toolkit, as I mentioned before. Root Toolkit has a diversity functionality, including data processing, statistical analysis, and visualization. This spectrum shows the full energy peak at our desired energy value, which is 662 kilo electron volts, with 7 kilo electron volts full width at half at maximum, after the Compton H at 473 kilo electron volts. So this is our conclusion. We can see our results in this table. As you can see, our Monte Carlo modeling of a perovskite gamma detector has 1.1% energy resolution and 29% photopeak efficiency. The energy resolution is similar to traditional detectors such as cadmium zinc telluride and thallium bromide. A lot of studies made such simulated bromine crystals small because it has a typical crystal growth condition, as we know. But we have 8 centimeter cube crystal now. There is no restriction in giant force space. We can make our crystal bigger, like 27 centimeter cube or 125 centimeter cube, even 1,000 centimeter cube. And we can see how properties change when they have a bigger size. And plus, because we can control our material compound, we can build up another perovskite structure or new structure materials. I believe it will be funny to compare them to our sesame bromide model now. This is our references, and thank you for watching my presentation. So if you have any question, please be my guest. So thank you.
Okay, thank you. Thank you very much. We have plenty of time. Okay, so thank you again, Charles. We can move to the next paper.
Okay, so, sure. Thank you, Alberto. And thank you very much, Charles, for your very interesting presentation. Thank you so much. So now we move on to paper number 3, which is entitled 2 realizations of the wearable PPG sensor working in reflectance mode for continual measurement in weak magnetic field. And this presentation is going to be delivered by Dr. Jiri Pribil from the Institute of Measurement Science from the Slovak Academy of Sciences in Bratislava. So Dr. Pribil, the floor is yours, and thank you very much.
Good morning, ladies and gentlemen. My name is Jiri Pribil. I am working in the Institute of Measurement Science, Slovak Academy of Sciences in Bratislava. I would like to present our work entitled 2 realization of wearable PPG sensor working in the reflectance mode for measurement in weak magnetic field. The structure of my presentation can be seen in the low part. The motivation of your work was to develop a wearable sensor based on the photoplethysmography or PPG principle for continual measurement in the weak magnetic field with the inherent radio frequency disturbance that exists in the scanning area of the running magnetic resonance imaging or MRI device. The sensor can monitor a mental or physiological state of the examined person during the MR scanning. Our final aim is to detect and suppress negative influence of vibration and acoustic noise, which is generated by the gradient system of the MRI equipment. In generally, a PPG sensor consists of 2 parts, a light sensor and a photodetector. The arrangement depends on the working mode. In the transmission mode, the light source and the photodetector are placed on the opposite side, as shown the left photo. PPG sensor working in the reflectance mode have the light source and the photodetector placed side by on the same body surface, as can be seen on the right photo. The variable sensors for real-time PPG signal measurement consist of three basic functional blocks. The first one is the basic analog interface integrated on the board together with the light source and the photodetector. The second one is a microcontroller, including an analog to digital converter. And the third one is the Bluetooth communication module for wireless data transfer to an external control device. The three photos below show the realization and practical usage of the optical PPG sensor working in the reflection mode. Both PPG sensor realizations are based on the optical pulse sensor Adafruit 1093 with an integrated basic analog interface, as was shown in the previous slide. Two prototypes differ in the Arduino board, sampling frequency, powering voltage, and mainly the used Bluetooth module. Details are shown on this slide. The PPG signal consists of the direct current or DC component and superimposed alternating current or AC components. The amplitude of the AC component is only about 2% of the DC one, but it follows the beating of the heart, so it is useful for the heart rate detection. As demonstrated on the graph on the right, every PPG cycle consists of systolic and diastolic peaks, which is giving useful information about the cardiovascular system. The PPG signal can be used to determine the heart rate values. The algorithm used for the real-time processing must be fast, simple, but robust and stable. Our algorithm works in 4 steps. First, the threshold level is determined from the PPG signal. Secondary, the binary clipping is applied on the pulse wave. In the third step, the pulse period, THP, are determined. And finally, the HR values are calculated. This process is demonstrated by a graphical example on the right. In the frame of post-processing operation, differential heart rate parameters are calculated using this simple equation. Then the statistical analysis is performed, including standard deviation and linear trends values for next comparison. Auxiliary experiment consists of 3 investigations. After the basic verification of PPG sensor functionality, measurement of sensors mean DC current for different types and supply voltages was realized. Next, we analyze influence on the length of the filtering window and the chosen sampling frequency on the precision and statistical stability of finally determined HR values. The main experiment was carried out in 3 phases. At first, we realized comparative measurement when the PPG signal pickup was accompanied with parallel sensing by the commercial oximeter device in normal laboratory conditions. In the second phase, we mapped the condition for wireless connection through the shielding cage of the open-air MRI device, where the last phase of our experiment was practically performed. As documented this slide, the shielding cage around the MRI device consists of the metal plates with the 2.5 millimeter diameter holes. So the wireless Bluetooth communication running at 2.4 gigahertz is principally possible. To prevent disturbance in electromagnetic compatibility inside the scanning area of the running MRI device, all parts of the PPG sensor must be covered by a non-ferrometric materials as documents 3 introduced photos below. There we can see an arrangement photo used for comparative measurement experiment. Parallel PPG signal recording by developed PPG sensors are accompanied with a commercial oximeter device with Bluetooth data transfer to the control tablet. The upper table shows differences in mean DC values for both tested sensors in 3 communication modes. In the case of the sensors with Bluetooth low energy communication module, the tested powering was used 2 types. The first one with 3.5 volts from USB stabilizer, and the second one by 3.7 volt by lithium polymer battery. Below are shown visualization of the influence of moving average filter on the final contour of the PPG wave. The auxiliary experiments next have shown that the higher sampling frequency can bring about the inaccuracy in the statistical analysis of HR values. It caused by the lower number of detected hair periods due to higher sampling frequency. The comparative measurement by the oximeter device shows that the first PPG sensorization has a higher variation of the differential HR values than the PPG sensor with low energy Bluetooth communication module. Because the PPG signals from the left hand was stronger than from the right hand, we prefer using the left hand's forefinger for the PPG signal sensing in the next experiments. There is shown the arrangement photo of the PPG signal sensing when a tested person is linked in the scanning area of the open-air MRI device. The body of sensor is mounted on the verst, as is documented by a detailed view. The screen copy of created control application for real-time sensing of PPG signal is shown on the right. Influence of the radio frequency disturbance of PPG signal sensing is demonstrated by 2 upper graphs. They practically confirm necessity of shielding all parts of the PPG sensor. Below are shown examples of PPG waves sensed in the scanning area of the MRI device without scanning activity. This is the graph on the left with running scanning sequence using the first realization of PPG sensor, this is the middle graph, and with running MR sequence using the PPG sensor realization with the low energy Bluetooth connection. Both sensor realization enable real-time PPG signal recording with the sampling frequencies from 100 to 500 Hz. But using sampling frequency higher than 250 Hz is reasonable only for determination of the systolic pulse with a high accuracy, because the window lengths for the moving average filter had influence on the amplitude and the width of the systolic pulses. The compromise setting of the window length equal 8 and the sampling frequency equal 125 Hz was finally chosen for use in our next experiments. Obtained results of comparative measurement by the oximeter device were already commented, so I will continue with the summary and conclusion. We can conclude that the both realization of variable PPG sensors are applicable for the current task. It means the real-time continual recording of the PPG wave in the scanning area of the running MRI device. Perform experiments verified functionality of the both sensors realization, but a few problems must be still solved. For example, influence of Bluetooth communication inside the running MRI device on the final quality of MRI device we must analyze in near future. It's all from me. Thank you for your attention.
Thank you very much, Dr. Pribil, for your very interesting presentation. I do have some curiosities, but I will also obey the rules and I will post them on the question and answers. So I remind everyone that the way in which we are going to be doing the questions and answers is that we will be having all of them at the end of the session, okay? So if anybody has any question, any comment in any of the presentations, please input the info in the question and answer slot that we have at Zoom, okay? So once again, Dr. Pribil, thank you very much for your interesting presentation. And now we can move on to our fourth paper. So Alberto, the floor is yours. Thank you.
Thanks, Francisco. Next paper is factory-oriented technique for thermal drift compensation in MEMS capacitive accelerometers. The presenter is from Spain, is Javier Martínez, which is with the Department of Electronic Engineering at the Escuela Universitaria Politécnica de la Almunia. Francisco, I hope that my pronunciation is okay, which is in Zaragoza, Spain. So please.
Okay, thank you very much.
Okay.
I am Javier Martínez, and together with Dr. Afzalaghaeinaeini and Dr. Bertrand, I'm studying the loss of performance in the application phases of microelectromechanical sensors. This work focuses on a lightweight technique for the thermal drift compensation in capacitive accelerometers. A MEMS capacitive accelerometer is based on a mass spring system connected to opposite plate capacitors. It detects a linear acceleration as a change in the capacitance. Those structures are made with silicon, which is a very temperature sensitive material. It has many advantages over traditional technologies, such as low cost, small size, and low energy consumption. However, one of its main disadvantages is the thermal drift it shows. It's linked to manufacturing imperfections, and therefore its values are random in each unit, requiring for an individual calibration. There are two main ways to compensate this effect. The first one is to reduce it with hardware techniques, such as alternative design of the internal structure, or using additional hardware, like for example, adding an external package that isolates the sensor from the exterior temperature variations. The other solutions consist of using software techniques, such as polynomial model or neural networks. The problem with these techniques is that they require a lot of data to be able to fit the polynomial or to train the neural networks, and this means a lot of time in each unit that needs to be calibrated. Our objective is to propose a lightweight compensation technique that requires less time. Also, we aim to reduce the equipment necessary to perform this calibration. If we reduce at all the laboratory equipment, we can allow the microcontroller to calibrate itself instead of sending the data to an external computer and then returning the calibration parameters. And this self-calibration has two main advantages. The first one is that multiple units can be calibrated at the same time, further reducing the calibration time. And the second is that any application board can be calibrated in field, allowing recalibration without expensive equipment. We base this work on this thermal model, where the difference between the real acceleration and the perceived acceleration is proportional to the temperature variation and depends on the temperature drift of bias and the temperature drift of scale factor. Having only two compensation parameters makes this model much easier to fit compared to surfaces, and also offers a lower compensation cost during the application phases. In a previous work, we compared this model to a second-order surface. In a second-order surface, the first phase for the comparison would be to eliminate the terms that do not depend on the temperature, as they will be calibrated with the mechanical calibration afterwards. And then the main difference between the two models is the second order of the temperature. However, experimental results show that there is a little effect of this parameter in the final calibration. Our approach to reduce the time is to minimize the number of positions and temperatures required during the test. We will do this by using all the positions to calibrate all the axes simultaneously, and we will use a contactless heat source that will reduce the thermal inertia of the system, further increasing the calibration speed. This contactless heat source also avoids any external forces. We will use the gravity force as our reference. Therefore, we need to avoid any extra stresses, and we will use only one anchor point between the board and the calibration structure. If we return to our model, we can see that for a fixed position where this x is constant, the change of the acceleration is directly proportional to the change in temperature. We call this the temperature drift coefficient, and can be used to interpolate the theoretical acceleration. Also, if we obtain two different temperature coefficients, we can split it in the thermal drift of bias and the thermal drift of scale factor and compensate the drift in all positions. As we only need two positions, we are gonna get the broadest range in all the three axes, and this is achieved with an acceleration of 577 milligis in each axis. This corresponds to a pitch angle of 55 degrees and a roll angle of 45 degrees. These are the two resultant positions, and we propose a simple calibration structure that is a plane that allows the user to quickly alternate between the two positions during the test. We also developed an algorithm that is able to compute these parameters in a microcontroller. It requires four segments, which corresponds to the two specified positions in a cold and a hot temperature each one. The order of these four segments does not affect the result of the calibration. After the data are captured, the algorithm checks if both the acceleration, the temperature, and the gradients of both is valid for the data to perform the calibration. Then it averages 1,000 values to ensure that all the noise is removed from the equation. Once all the four segments are obtained, it directly gives the user the thermal drift of bias and the thermal drift of scale factor to perform the compensations during the application. Comparing this technique with other traditional techniques, our calibration time is reduced to only 2 hours after the device is powered up. If the device has already powered up, the calibration time can be 1 hour and a half. Also, the compensation time is only in the microcontroller tested 25 microseconds. Other traditional technologies require up to 40 hours or more to obtain all the necessary data for the polynomial fitting. And during the compensation phase, they also require more time. The other main advantages of this technique is that it requires much less equipment, only one heat source to offer a second temperature point other than the ambient temperature is needed, whereas other techniques require a thermally controlled environment or a thermally and position control environment. However, the accuracy of this compensation is similar to those of more complex techniques. We check that the proposed algorithm can be run in 2 popular microcontrollers or using only from 3 to 5 kilobytes of program memory and around 500 bytes of data memory. Most of this data memory can be freed after the calibration. We also decide to compare this technique using only two positions and 2 temperature points with a more traditional technique using 6 positions and a greater range of temperatures. And with the same model, the maximum difference we obtained was 0.06 millijoules per degree. And in the compensation phase, we can see that there is a great difference between the uncompensated model and the 2 compensation techniques. However, both compensations are pretty similar. In general, we think that the proposed model characterizes the thermal drift in a range very similar to techniques that require a lot more of points and therefore a lot more time. And our techniques allow for a simultaneous calibration of units and in-field calibration or recalibration. We think that this technique is most interesting to factory environments where mass productions requiring individual calibration can make the cost of the products go high really fast. Thank you for your attention.
Thank you for your very interesting presentation. So I invite participants to write questions in the Q&A window. And so we can now move to the next and last presenter.
Thank you very much, Alberto. And thank you very much, Javier, for your very interesting presentation as well. And so now we're going to move on to paper number 5. And it is entitled Design of a LIOR-based DDoS filter for LiDAR sensors in off-road vehicles. And it will be presented by Ali Afzalaghaeinaeini. I'm sorry if I said this wrong, really sorry, which is a researcher at Ontario Tech University. So Ali, please, the floor is yours. Thank you very much.
Hello, everyone. I hope you are all doing well. And as the professor said, my name is Ali, and I'm happy to be here for presenting our work, which is design of a LIOR-based DDoS filter for LiDAR sensors in off-road vehicles. And yeah, here is the summary of what I want to present today. And at first, we want to introduce our topic and then review some of the literatures about that. And after that, we want to explain in detail our project methodology and discuss our results. And finally, we will end up with a conclusion and what we want to do in future. First of all, I want to mention that LiDAR sensors provide a very rich information about the environment. Some of the facts about the LiDAR sensor which we are using is, for example, up to 300,000 points per second can be created by Vallan VLP16, which you can see the image in this slide. And here is the results or visualizations of the data points captured by this sensor. And each point contains some of the information like X, Y, Z coordinates of each point, and also intensity of the objects detected by LiDAR. And these informations can be used in a variety of tasks like localization and mapping, obstacle avoidance, and so on. But the problem is that the performance of this sensor degrades hugely under adverse weather conditions, like including dust and other adverse weather conditions, also like snow. And this fact caused some problem in the data acquisitions, and this problem will lead to misperception, and this misperception can make the whole perception of the robots or the vehicles prone to failure. You can see in this slide a picture of a scene with a dust, as you can see in here. Here is a human, tree, an object, and here is a dust that's created by human. And as you can see, here is the corresponding point cloud. And you can see that here there is no difference between the human and the dust. So the dust can be perceived as a human or object. So this is a problem that we want to solve. If I want to talk about some of the related work about dedusting, I can talk about these literatures. First of all, there are some conventional methods, including ROR methods. The first paper, which is denoising of LiDAR point clouds corrupted by snowfall, is try to improve the ROR filter for the snowing, and they showed that the developed filter works well for the case of the snow. And there is another paper on 2020, which again developed a two-step filtering that works based on the intensity. They also showed that a good performance for snow. And for the case of dots, we have seen some methods based on machine learning methods and AI methods. For example, in 2018, some methods like SVM or support vector machine and random forest and neural network has been applied to this area. And also in the 2021, the deep learning methods also has been applied to this area. And so the question is that what we want to, let me explain in more detail another paper which our work is based on this paper. And this paper named fast and accurate designing algorithm of LiDAR point clouds, which they proposed a LIOR method. The LIOR method works based on two simple principles. The first one is it selects the points with intensity values below the specified threshold, and this specified threshold is important in this filter, and we will discuss more in the following slides that how we have to find this threshold. And after that, in the second stage, it applies radius outlier removal filter to these selected points. And the reason, and after that, those points that are identified as outlier in the second stage are removed as outlier. Otherwise, they are in layer. The summary of what I discussed in here can be seen in here. And I want to explain more about the radius outlier removal filter in here. The radius outlier filter involves three main parameters, including the N, M, SR, which are the number of neighbors found within a search radius, minimum number of neighbors, and also search radius. Let me explain it in this picture. For example, this filter, it rates for every point, for example, this point, and for this point, it will count the number of the points inside this circle. This circle has a search radius, a specific radius we call search radius. And if this the number of points is less than the minimum number of neighbors, then it will be detected as outlier. Yeah, the summary of the filter, working principle of the filter. So the question is what we wanted to do about this topic, and our research objective can be summarized in here. There are two main issues with the current literature. The first one is that the AI techniques have two limitations. The first one is they are hugely dependent on the training set. So if you have a low quality of the training set, then you won't have a good result. And the second one is they are computationally so expensive to develop. And sometimes you need some supercomputer to train your model, especially in the case of LiDAR, where you have a lot of data set. And also, for the traditional methods, to the best of our knowledge, none of the non-AI technique developed for the dusting. So there is a gap between the AI technique and non-AI technique. And this study developed non-AI technique based on LIR method, which is easy to implement in practice. Okay, now in this slide, you can see a summary of our project methodology. In the first stage, we have to acquire the data or raw point cloud from the LiDAR sensor. In the second step, here is our LIR method with the three main parameters that we want to tune these parameters. So the output of the LIR method is a classified point cloud. By classified, I mean it will either remove the points or classify it as in layer. And to know how well our filtering has been done, we have to have some evaluation metrics to understand it. And then after that, we will tune our parameters and find the optimum values for this filter. Okay, in this slide, I want to talk about our evaluation metrics. We use some of the common metrics used for filtering methods and also AI methods, including accuracy, precision, recall, and F1 score. And these are so common in the literature, and we use too. And if we want to talk more about these metrics, first I have to introduce the these values, for example, TP, TN, FP, and FN. And TP is the number of DOS points that predicted truly, and TN is the number of non-DOS points that predicted truly, and also FP is the number of DOS points that predicted falsely, and FN is number of non-DOS points that predicted falsely. Or yeah. And here is a confusion matrix, and which can be explained more this concept in here. We have in one axis a true value, for example, and in another axis is a predicted value. For example, in total, for this example, we have 24 points which predicted truly based on here, non-DOS points truly, and 1 points which are misclassified, and so on. And based on this value, we can compute these metrics, I mean accuracy, precision, recall, and F1 score. When we have a high F1 score, it means that our accuracy of classification is very high. So there are three parameters in the LIR methods that needs to be tuned. The first and the most important one is the threshold intensity that we use for the first part. To choose a correct value for this, we gathered a dusty data set, and this data set contains 18 packets of data, and each packets have 60 point cloud data. And to know which point is DOS or non-DOS, we need to label our data, and after that we analyze the DOS data intensity. Here is the summary of that. You can see based on this figure that most of the non-DOS, most of the DOS points have an intensity lower than 8. In the x-axis is the intensity value, and in the y-axis is the number of the points. And you can see that there is a very limited number of points for non-DOS that the intensity is lower than 10. So based on the analysis of these figures, we came to conclusion that we have to choose the threshold intensity as 7. And yeah, for the rest of the parameters, we choose a range of values and for them. And after that, we try different values for these parameters. And in the table 1, we have shown the optimized LIR parameters, which works well for the dust conditions. The threshold intensity is 7, radius search is 0.044, and the cutoff value is 6. Okay, and here is the results of our work. As you can see in here, we have some dots. Here is the human, and after that, we can see the DOS has been completely removed. So, which means this filter works well. But if we want to be more accurate with our results, we also provided in the table 2 the summary of our results. We applied our filter to 1 packet of data, including 90 point clouds. The metrics for each point clouds calculated and shown in here. Here is the mean value of all 90 point clouds for all of the metrics. And we can see that the mean value for F1 score is 82.88, which is a very good value. So if I want to conclude, our work, I have to say that we propose a dedusting filter based on LIR technique, and after that we validated our results through 4 different metrics, and the limitation of our current work is that this filter removes some non-dust points that have low intensity, so this is the disadvantage of that. And besides, it misses minor dust points which their intensity is more than the threshold intensity. But a great thing about our work is that this approach takes advantage of simplicity and can be applied easily in practice. Our future work could be changing the filter used as a second step in LIOR, and we can also implement our work in real time and see how robust it is in practice and compare our work to some of the machine learning algorithms. Here is the a list of our references, and thank you for your attention. If you have any questions, please let me know.
So thank you, Ali, very much for your very interesting presentation. And thank you for being awake so late or early. I don't know how to express it. And so I think that now we are in the point of the session where we can open the question and answer. So now we have the first answer, or sorry, the first question. And this one was posted by Javier, and he says the following. He says, "Hi, Sebastian, thanks for your presentation. My question is if there would be interesting to control the heater temperature in a closed loop to keep the heater temperature close to the set point and avoid the drop in performance due to temperature drift." So yeah, Sebastian, I think this one is for you.
Yeah,
So,
thanks a lot for the question. Yeah, so basically, if I understood it correctly, this closed loop was intended, or the suggestion was intended for temperature drift over time. So that we have a closed loop that kind of keeps the temperature at the same level. This was not exactly the problem that we were dealing, that I was dealing with the simulation study. So there it was more about that the temperatures are constant, but they have a little bit of an offset due to production, for example, like the initial calibration. And therefore, I'm not sure if a closed loop would help in this regard, but it's definitely an interesting, an interesting suggestion if there would also be like a problem with a temperature drift in general. But as far as I saw it up to this point, this was not the case, and therefore, yeah, I'm not sure if this suggestion is suitable for the problem that for the research question that I presented.
thank you, Sebastian, very much. So, do we have any more questions? Please don't be shy and feel free to pose questions. In the meantime, while people want to make a question, I had a curiosity in relation with the work presented by Dr. Pribil in relation with the measurement of the pressure sensors and the blood pressure sensors and so on. Very interesting. Doctor, you stated that the results were received better using the left hand instead of the right hand, I think. Is there any reason for that? It's just curiosity.
In my opinion, it's not curiosity. It can be caused because the left hand is near the heart. Right. There's the changes in the human cardiovascular system can more influence it on the left hand. We test also the type of finger. The problem with the affection sensor is that we must receive some well response of the to the photodetector from the light source. It does mean where is the core of the finger to match with, for example, on the 5 finger, we cannot receive the well response. Therefore, we use the forefinger one for the sensing the signals.
Okay, thank you very much. Thank you.
Okay, I have a question for Pribil, Dr. Pribil. You have demonstrated that your shielding is effective when the system is working near the MRI facility, right? And I'm wondering what is the part of your system that is sensitive to the disturbance, the photodetector, amplifier, or what else? So what is really important to shield in your system?
It follows from the functionality of the whole MRI equipment. There exists the one part which is called the gradient system, which consists of 2 X, Y, and Z coils, which is excited by the high current pulses, which produced during the scan some mechanical vibration. There is causing the magnetostriction principle. This one problem. The second one is the excitation of the spin. It is the principle of magnetic resonance imaging. By the high frequency, this device works with the 10 megahertz as the working frequency, excitation radio frequency coils. It is the second type of distribution. In this environment, all classical sensors or electronic without the shielding cannot run or can be destroyed, as is our
okay, so the whole system must be shielded. The whole system.
Yes.
Okay, I understand. Thank you. And I have a question for Sebastian. Do you train the neural network with information about temperature or not? I missed this point.
So basically, there's no information on temperature there.
Okay, and could be useful to feed the network with the temperature information.
I mean, if there would be like additional data available with a temperature sensor, for example, that would be the case. Yeah, but in the setup that I simulated, this wasn't additional data that was available for the sensor. But that would also be something to consider. Yes, that's a good suggestion.
Because maybe there is a temperature sensor somewhere in your system, so it's possible to take advantage of this information.
Yeah, definitely.
Okay, thank you. Thank you again.
So I have one more question. I would like to ask Ali, since you're awake, right, at this time of the night, well, it would be nice to have some question. I was curious in relation with what you foresee as the final application, because you mentioned that you can use it for off-road vehicles in dusty conditions, or you could use it maybe in industrial environments. Could you elaborate a little bit more on that? Because I'm really curious on how you're going to use your algorithm. So,
first of all, thank you, Professor, for your consideration. And if I want to explain more, these techniques can be applied to any applications that involves dust. I mean, for example, one robot which is working in a dusty conditions, maybe agricultural robot, something like that, can you take advantage of this filter too? Because as I mentioned at the first of my presentations, every place that used a LiDAR can use our filter, because this LiDAR sensor performance degrades under dusty conditions. So these filters help to dedust the point cloud, and yeah, I don't know whether I can answer your question well or not.
The thing, yeah, for sure. The thing is the following. For example, in the applications that you are commenting, I guess that your robots are moving at a relatively low speed. That is, my question is trying to, in some way, relate what is your processing time and what is your reaction time of the algorithm as applied to your LiDAR. Because imagine that you are talking about a robot which is moving at a relatively low speed, I assume, versus, for example, an off-road vehicle that can be moving at a relatively high vehicular speed. So I guess that could pose some constraints and challenges to the algorithm. So that the question is in that sense.
Yes, I understood. And actually, for this paper, we didn't measure the time for, but the roughly time for prediction of one point cloud would be something like 0.1 second. So I mean that if the speed is not very high, this filter can be applied, because yeah.
Okay, sure, yeah, for sure. Okay,
but
thank you.
For future, I guess that it would be a very good idea to consider the time constraints of this filter too.
For sure, I'm looking forward to seeing what you can achieve with that. For sure, it's really interesting. Thank you very much.
Thank you too.
But do you process a single image in your dedusting algorithm? So a single acquisition, or you take advantage of different acquisition, since the noise effect, the dust effect is something like a random process. So I'm thinking about the process subsequent acquisition in order to better understand what is dust and what is not dust.
Yes, actually, this data consists of two different data acquisitions. I mean, for different days.
Okay.
Yeah, and each day has a multiple. I mean, data acquisitions. I mean, it is not a one.
Okay.
Yeah.
Okay. Clear.
No problem.
Okay, any further questions? Well, I also have another curiosity, if possible. I would like to ask Javier in relation with the technique that has been proposed in relation for the thermal compensation, right? So my question is again on application. While you have developed this, let's say, simple method to provide the calibration for the sensors, which is really interesting, were you thinking of any specific application in mind? Was it application oriented? Was it a general purpose algorithm? What do you think?
Well, thank you for your question. The first application was the use of accelerometers as inclinometers, where the precision is vital. And if it's in the outside, the temperature variation from day to night could lead to variations up to 3 or 4 degrees.
Okay.
But as the compensation technique is pretty fast, only 25 microseconds, we think it can be applied to any acceleration application.
Okay, very interesting. Yeah, I was thinking of something of the sort, because when I was seeing I was saying, oh, maybe they want to use it in an outdoor application with thermal drifts and so on. Okay. So, and are you thinking of using it, for example, for, imagine, a purpose-based accelerometer coupled to the corresponding microelectronics coupled to whatever sensor? Or for example, would you consider using an opportunistic sensor, like it could be, for example, an accelerometer embedded in a smartphone, so you can also use it as a sensor? It would be more related to the first application, I guess so, but could it maybe also be used to enhance angle and vector positions using a smartphone, for example, do you think, or wouldn't it be useful at all?
Well, I think it can be useful in all applications. We have seen that the thermal drift is a real problem in all cases. So as long as there is a temperature variation, you need to compensate that effect. I see in acceleration, the effect can be up to 50 millig's. That in many applications, for example, with the smartphone, could not be a real problem, but another application, like for example, tilt measurements or slope measurements, it can be really interesting. So we are more thinking in outside monitoring applications, but I think it can be applied to any kind of application.
Okay, thank you, Javier. Thank you very much.
I have a question for Javier. How did you choose the angles? So I'm thinking about if there is an optimization process behind your angle choice.
So we need to find a 577 millig's in each axis. So in all three at the same time. So with that value, we can obtain the pitch angle, and that is divided by the gravity vector, which will be our only source of force.
Okay.
And that leads to a 55 degrees in pitch. And then we can use that 55 degrees to obtain the second rotation, that is a roll of 45 angles. Okay,
I understand. Okay. And where do you measure temperature? On the sensor or in the room?
No, in the sensor. Most of the sensors have embedded temperature sensors because this is a real problem. So the manufacturer already accounts for that.
Okay, thank you.
Yeah, so I also have one question for Charles, if possible. Very interesting, the work in relation with the simulation of the radiation detection. Now, my question is, you presented very interesting simulation results. Any plans to measure this and use it in any specific radiation detection applications like the one you mentioned?
First of all, thank you for question from me. So we'd like to make our digital model have a bigger size than traditional models. So actually, usually perovskite structure detector model, perovskite detector is usually 1 to 3 centimeter cube now, but we want to make the bigger size, like 10,000 centimeter cube, like really huge. So you can see how much change they have. Energy resolution or photopeak efficiency. So and we want to try another structure like sodium lead bromide with iodine or zinc. Yeah, we will try later. After this. Yeah. So it is a simulation data, so we can make on the jet for space. So we will see.
Okay, I see. Okay, sure. So looking forward to see the progress for sure on the next ECSA. We'll see how it goes. Okay.
Not this time.
Thank you very much, Charles.
Thank you very much.
Charles is concerning your numerical model. Have you found any sensitivity of your numerical model to the dimension of the crystal and to the shape of the crystal?
So actually, yeah. So
numerical. I mean numerical problems related, maybe the mesh or the Monte Carlo.
Yeah. So actually, in the geometry simulation, it is hard to find that way. So we'll create detect the model in our lab now. So yeah, we'll see that too later.
Okay.
Yeah, thank
you. Thank you.
Okay, so everyone, we're actually on time, 10 past 11. So I wish to thank you, each and every one of you, for your time. And I think that we've had a really, really wonderful session. I think that the results presented are really fascinating, really interesting. So once again, I would like to thank you all for your time and your consideration and contributing to ECSA. I wish you all the very best, and for sure, I hope that you can continue participating and collaborating with ECSA to make it the success it is. So thank you once again. Again, I wish you all the very best. I wish you all to have a good night's sleep in some cases and a very good day for all the rest of you. So thank you very much. Thank you.
Thank you to the authors.
Just a few words from my side. I would also like to thank the chairs and the speakers for their time and interesting contributions to this webinar. Also, I thank you to our attendees. I hope you found this webinar interesting. As a reminder, the recording of the webinar will be made available as soon as possible on the webinar's webpage, on the conference webpage. I wish everyone a nice day, morning or evening, wherever you are in the world. Stay safe. Bye.
Thank you, everybody. Take care. Bye-bye.
Bye-bye.